Welcome back. So where we left off in the last video, I had shown you this thing called the geometric series, and we could have some base a. It could be any number. It could be it could be 1/2. It could be 10. But that's just what some number, and we keep taking it to increasing exponents, and we sum them up, and this is called a geometric series. And so I want to figure out the sum of a geometric series for when I have some base a and I go up to some number a to the n. Why did this a to the What did I write a to n minus 2 there? That should be a to the big N. Oh yeah, my brain must have been malfunctioning in the previous video. That always happens when I start running out of time. But anyway, let's go back to this. So I defined S as this geometric sum. Now I'm going to define another sum, and that sum is I'm going to define as A times S. A times S, and that equals, well, that's just going to be A times this exact sum, right? So, and that's the same A as this A, right? That A is the same as this A. So what's A times this whole thing? Well, it's the A times A to the 0 is, well, let me write it down for you. So this will be A, because I just distribute the A, right? A times A to the 0 plus A times A to the 1 plus A times A squared plus all the way A times A to the n minus 1 plus A times A to the n, right? I just took an A and I distributed it along this whole sum. But what is this equal to? Well, this is equal to A times A to the 0, that's A1, A to the first power, plus A squared, plus A cubed, plus A to the n, right? Because this is, you just add the exponents, A to the n, plus A to the n plus 1. So this is AS. And we saw before that S is just the original sum. That is just A to the 0 plus A to the 1 plus A squared plus all the way to plus A to the n, right? So let me ask you a question. What happens if I subtract this from that? What happens if I say AS minus S? Well, I subtracted this from here on the left-hand side. What happens on the right-hand side? Well, all of these become negative, right? Let me do it in a bold color. This becomes, because I'm subtracting, negative, negative. These are all negatives, negative, negative. Well, A to the first minus A to the first, that crosses out. A squared minus A squared crosses out. A to the third. It'll all cross out even all the way up to A to the n, right? So what are we left with? We're just left with minus A to the 0, right? We're just left with that term. And we're just left with that term plus A to the n plus 1. And of course, what's A to the 0? That's just 1. So we have A to the S, not A to the S, A times S minus S is equal to A to the n plus 1 minus 1. And now let's distribute the S out. So we get S times A minus 1 is equal to A to the n plus 1 minus 1, right? And then what do we get? Well, we can just divide both sides by A minus 1. Let me erase some of this stuff on top. Erase. I think I can safely erase all of this, really. Oh, I don't want to erase that much. I want to erase this stuff. That's good enough. Okay. So I have just dividing both sides of this equation by A minus 1, I get S is equal to A to the n plus 1 minus 1 over A minus 1. So, where did that get us? Well, we defined the geometric series S as equal to the sum from k is equal to 0 to n of A to the k, and now we've just derived a formula for what that sum ends up being. Equals A to the n plus 1 minus 1 over a minus 1. And why is this useful? Well, we now know, if I were to say, well, what is, let me clean up all of this as well. Let me clean up all of this so we can, okay. So if I said, you figure out the sum of, I don't know, the powers of 3 up to 3 to the, I don't know, 3 to the 10th power. So, 3, so 3 to the 0 plus 3 to the 1 plus 3 squared plus all the way to 3 to the 10th. So this is the same thing as a sum of k equals 0 to n of 3, to 10 of 3 to the k, right? So this formula we just figured out, a is 3 and n is 10. So this sum is just going to be equal to 3 to the 11th power minus 1 over 3 minus 1, which equals, well, I don't know what 3 to the 11th power is, minus 1 over 2. So that's kind of useful. That is a number, although you'd have to memorize your exponent tables to the 11th power to do that. But I think you get the idea. This is especially useful if we were dealing with, well, if the base was a power of 10, it would be very, very easy. But what I actually want to do now is I want to take this and say, well, what happens if n goes to infinity? Let me show you. So what happens? So there's two types of series that we can take. That's not what I wanted to do. There are two types of series that we can take that we can find the sums of. There's finite series and infinite series. And in order for an infinite series to come up to a sum that's not infinity, they need to, what we say, they need to converge. And if you think about what has to happen for them to converge is every next digit has to essentially get smaller and smaller and smaller as we go towards infinity. So let's say that a is, I don't know, let's say it's a fraction. A is 1/2. So how does the geometric series look like if we have 1/2 there? So let's say that we're taking the geometric series from k is equal to 0 to infinity. So this is neat. We're going to take an infinite sum, an infinite number of terms, and let's see if we can actually get an actual number. We take an infinite things added up, and it actually adds up to a finite thing. This has always amazed me. And the base now is going to be 1/2. It's 1/2, and it's going to be 1/2 to the k power. So this is going to be what? 1/2 to the 0 plus 1/2 plus, what's 1/2 squared? Plus 1/4 plus 1/8 plus 1/16. So as you see, each term is getting a lot smaller, right? It's getting half of the previous term. So what happens? Well, let's say, what happens if this wasn't infinity? What happens if this was n? Well, then we would get plus 1 over 2 to the n, right? 1/2 to the n is the same thing as 1 over 2 to the n. And if we looked at the formula we figured out, well, we would say, well, that is just equal to 1/2 to the n plus 1 minus 1 over 1/2 minus 1. And that would be our answer. I mean, we'd have to know what n is. But now we want to know what happens as we go to infinity. So this is essentially a limit problem. What happens? What's the limit as n goes to infinity of 1/2 to the n plus 1 minus 1 over 1/2 minus 1? Well, all of these are constant terms, so nothing happens. So what happens is this term right here goes to infinity. What's 1/2 to the infinity power? Well, that's 0. That's an unbelievably small number. Take 1/2 to arbitrarily large exponents. This just goes to 0. And so what are we left with? We're just left with this equals minus 1 over 1/2 minus 1. Or we could multiply the top and the bottom by -1, and we get 1 over 1 minus 1/2, which equals 1 over 1/2, which is equal to 2. I find that amazing. If I add 0 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and I never stop, I go to infinity. Not infinity, but I go to 1 over, essentially 2 to the infinity. I end up with this neat and clean number 2. And this might be a little project for you to actually draw it out and to, like maybe a pie, and see what happens as you keep adding smaller and smaller pieces to the pie. But it never ceases to amaze me that I added an infinite number of terms, right? This was infinity, and I got a finite number. Anyway, ran out of time. See you soon.